Okay, this section is on factors of integers and polynomials. So we're going to be looking at numbers that have factors that are factorable, and then also looking at polynomials that are factorable. And the reason we're starting with integers and then moving to polynomials is because factors of integers and factors of polynomials have many of the same properties. So they behave similarly. So that's why we're going to look at just integers and then upgrade that to polynomials. So they have many of the same properties. Not enough room, sorry. So the definition of a polynomial right here is that for any non-negative integer n, a polynomial in x, meaning in terms of the variable x, is an expression that looks like this. P of x, which should look familiar, equals a sub n, which is just going to be some coefficient of the variable x to the n, plus some other number, coefficient a sub n minus 1 times x raised to the n minus 1 plus, and this will continue all the way down until that coefficient, instead of n minus 1, until that exponent, is 0, meaning just a constant. So the second to last one would just be a1 times x raised to the first power plus a naught, or a to the 0 power, or a sub 0 times x to the 0, but x to the 0 is just 1, leaving this last term as just a constant. Now this is a very complex and almost confusing way of defining a polynomial, because instead of actual numbers, all of these a sub n's would be numbers, integers, and all of these powers would just be powers. Say you were looking at a fifth power polynomial, that would be a 5, that would be a 4, and then 3 in between, and then 2, 1, 0. So right here we see this box of polynomial vocabulary. We do have names for the first 5 or 6 polynomials based off of what their highest degree is. So we use the term or phrase degree of a polynomial right here. It means the highest degree of the highest exponent in that polynomial. So the 0 polynomial is just p of x equals 0. It's just literally equal to the number 0. A constant polynomial is what we call the polynomial that doesn't have any variables. It's just a constant number. For example, p of x equals 6. That's a constant polynomial. That function would just be a horizontal line at y equals 6. A linear polynomial, also known as a line, it looks funky, but you can relate that to y equals mx plus b. The slope would be a1, x is x, and then a naught would be the y-intercept. So it just looks different here, but that's a linear polynomial and is of degree 1. And going back, the constant polynomial is degree 0. The quadratic polynomial you should all be very familiar with and should remember that it is a degree 2 polynomial. A degree 3 polynomial is a cubic. Degree 4 polynomial is a quartic. And degree 5 is a quintic. So those are just a few vocab words. You don't need to memorize those. They make sense though if you just think of what those numbers mean. You will hear me refer to a polynomial either in its factored form or expanded form, which we'll talk about right here. So the factored form of a polynomial is exactly what you would imagine, and that would be the factored form of a polynomial. For example, the polynomial p of x equals x times x minus 4 times x plus 2. that is the factored form of some polynomial, and I could write the expanded form of that same polynomial by multiplying, distributing everything through. So I would first FOIL these two, and then eventually multiply this x through to everything. And when doing that, we would get the expanded form, which I'll just tell you is x cubed minus 2x squared minus 8x. So it makes sense, but just be aware that we'll both be talking about factored form and expanded form of a polynomial. All right, when you add, subtract, or multiply two integers, what you get is another integer. And polynomials behave in the same way. If you add, subtract, or multiply two polynomials, you will get the resultant polynomial. So you'll get another polynomial. The reason I make that point, polynomial. That means that integers and polynomials are closed, and we talked a little bit about this with integers once before. That's an O. Closed under addition, subtraction, and multiplication. So being closed under an operation, and remember these are operations, being closed under an operation just means any combination using those operations results in another integer or another polynomial. However, they are not closed under division. Why not? Because just because I have two integers, for example, 2 is an integer and 3 is an integer, but when I divide them, 2/3 is not an integer. That's a rational number, but it's not an integer. Same thing with polynomials. So they're not closed under division. Okay, now we're going to look at the formal definition of a factor. We use the word factor all the time. Greatest common factor, least common factor, what's a factor of this? We're going to factor this polynomial. So we use the word factor all the time. Now we're going to define it formally. So n and d, it's important to keep those different in our minds. So we're saying that d is a factor of n. D is a factor of n if and only if there exists, so backwards e means there exists an integer named, we'll call it q. So d is a factor of n if and only if there exists some integer q such that such that n is equal to the product of d times q. And this should make sense because if d is a factor, if d is a factor of n, then n equals d times some other number. So for just a quick example, I could say, how do I know that 4 is a factor of 12? Well, because I can write 12 as 4 times some other number. In fact, that number q would be 3. So something is a factor, that's my something, is a factor of a number n if and only if that n can be represented as the factor times q. Same thing goes for polynomials, except instead of d and n, we have d of x and n of x. So d of x is a factor of n of x if and only if there exists a polynomial q of x such that, same thing, n of x equals that factor d of x times some other factor q of x. So q of x and q, those are just other factors of n. Now there's lots of other ways to say that something is a factor. So this right here is saying that d is a factor of n. It's also saying q is a factor of n. But let me use an actual example. So for example, 6 equals 2 times 3. That right there is proof that 2 is a factor of 6 and also 3 is a factor of 6. But another way There's 4 different ways. All of these ways we can describe that relationship. We can also say n is a multiple of d, or 6 is a multiple of 2. We could also say n is divisible by d, or 6 is divisible by 2. D is a factor of n, so that's what we've been saying. Or Q is the quotient when n is divided by d. These 4 things all mean the same thing. These 4 things, if you have any of these descriptors for n and d, that means this relationship exists. So you guys are going to need to be able to use this definition of a factor to prove that something is a factor of something, or to prove that some number is divisible from other numbers. So if you look at example 1 on the second page, we see 8 is a factor of 56 because. Well, how can I prove that 8 is a factor of 56? Well, the number n is 56, d would be my factor. I need to show that this relationship exists. So if I want to show that 8 is a factor of 56, I need to show that 56 equals 8 times some number q. Well, to get that number q, I could just divide both sides by 8, and if q is an integer, then it works. And we hopefully know that 56 divided by 8 is 7. So because 56 equals 8 times 7, 8 is a factor of 56. Same with 117 is a multiple of 13. So we're just rewording it, but we still need to go back to this relationship. So if negative 117 is a multiple of 13, then I should be able to write it as 13 times some number q. So you just grab your calculator and divide. Negative 117 divided by 13. You get negative 9. So we've just shown that, in fact, it is a multiple of 13. 5 is a factor of negative 5 because. So 5 is the factor of our number n. We switch colors. So n would be negative 5 equals our factor 5 times some other integer, which is just negative 1. So it seems simple, but this is using this definition, that relationship, to prove that things are factors of other numbers. And this last one here says 4 is not a factor of 58 because, now remember, if 4 were a factor of 58, we would need to show that 58 equals 4 times q. But when you divide by 4 on each side to get q, to figure out what q is not an integer. It's a decimal, which means it's a rational number, not an integer. So no integer satisfies No integer satisfies 58, this equation, 58 equals 4 times q. There is no such integer q to make that true. So 4 is not an integer or a factor of 58. So we're going to take that same relationship and that same definition of factor and just start applying it to polynomials or more complex equations. So you see here in example 2, is 3 a factor of 3m minus 6n? Yes, we all know that it is because we can factor a 3 out of that. But we just have to show, so I'm going to use the letters W, T, S, want to show that if 3 is a factor of 3m minus 6n, then we want to show that 3m minus 6n equals 3 times q, where q is some integer. So we can do that because we know that 3m minus 6n really equals 3 times m minus 2n. So is that enough? Can we be sure that this is an integer? Because that's what we needed. That's our q. Is m minus 2n an integer? Well, I did a bad job in this example because I didn't say that m and n were integers, but they are. So if m and n are integers, m and n are integers, and remember, integers are closed under addition, subtraction, and multiplication. So m minus 2n is also an integer. Therefore, yes, 3 is a factor of 3m minus 6n. The important part was showing this relationship exists, and then we just had to clarify that that right there is an integer. So example 3, it's worded in a different way. It's saying that 7m squared n cubed is a multiple of mn to the 5th. If that's true, then we would want to show that 7m squared n cubed equals some number times that, mn to the 5th times some integer q. Excuse me. So if that were true, well, how would we figure out what q is? Well, we would divide both sides. This would imply that q equaled, and then we would just divide 7m squared n cubed divided by mn to the 5th. So if that were true, that's what q would have to equal. But what just happened is we took these integers. We know m and n are integers, so that's an integer. M times n to the 5th would also be an integer. Does that necessarily mean that their quotient is an integer? And we saw that integers are not closed under division. So because this is not always an integer, we cannot conclude that that's a multiple of mn to the 5th. So no, we can't be sure of that. It depends on what m and n are. And then lastly, it's saying, example 4 here, is x plus 5 a factor of x squared minus 225? So this is our d. We're applying this same concept, n equals d times q, to polynomials now. So this is our n of x. We want to show that n of x, which is x squared minus 225, equals d x plus 15 times some other polynomial. Is there another polynomial that we can multiply times x plus 15 to equal x squared minus 225? Well, x squared minus 225 happens to be a difference of squares, which means, yes, it is a multiple of x plus 15, because if we multiply x plus 15 by x minus 15, we get x squared minus 225. So the answer to that question is yes, it is. Okay, this next example is going to lead into a couple of theorems about integers and polynomials. So just to introduce the theorems, we'll just do this example 5 just to help it all make sense. So 3 is a factor of 6, which is true, and 6 is a factor of 12. So 3 is a factor of 6, but 6 also happens to be a factor of 12. Then we can conclude that 3 is a factor of 12, which should make sense. But that is the transitive property of integer divisibility, which is a lot of big words, but really it's just saying that if you have one number that's a factor of some other number, but that some other number is a factor of an even larger number, then that first original must also be a factor of that larger one. So if you have integers a, b, and c, a is a factor of b is a factor of c, then a is a factor of c. And the same thing applies to polynomials. So you a of x, b of x, and c of x. If a of x is a factor of b of x is a factor of c of x, then a of x is also a factor of c of x. the proof for this is kind of cool, and you can definitely follow along. I know you all cringe at the sound of the word proof, but a proof is just convincing the reader that something is true. So we're going to convince ourselves that given A is a factor of B, that's one piece of given information, and B is a factor of C. Those two pieces of highlighted red are what we can assume is true, and then we hope to show that A is a factor of C. Now, given A is a factor of B, if A is a factor of B, then we can say B equals A times some other integer, we'll call it M. And if B is a factor of C, that means C equals B times some other integer, we'll call it N. So that must be true. Remember, these are given pieces of information. So that's given, which means this has to be true by definition of a factor. If B is a factor of C, then C equals B times some other number. We want to prove A is a factor of C. Well, if we know C equals B times N, remember I have this other way of representing B over here. So, excuse me, I'm going to plug in AM for B because it equals that over here. So instead of B, I can write A times M times N. So really what I have is C equals A times M times N, and Mn is an integer. So right here I've just represented the fact that C equals A times an integer, which proves that. So we're done. Therefore, A is a factor of C. So simple proof to show that. So these examples are pretty straightforward. So if 13 is a factor of 1001, but we also know 1001 is a factor of that, then we can use the transitive property that above to say that 13, therefore 13 is a factor of 364,364. Same thing with example 6. We know 6 is a factor of 12. We also know 12 is a factor of 144. So then we can conclude that 6 must also be a factor of 144. And then we can relate the same thing to polynomials. 2 is a factor of 2x plus 2. But 2x plus 2 is also a factor of that polynomial, so then we can link that first one and that last one together. 2 is a factor of that whole thing, 2x squared plus 4x plus 2. So these are all just demonstrations of these transitive properties. Okay, on this last page, similar to that transitive property, the factor of an integer sum. So I'll give you the definitions and then we'll go over an example so it makes sense. So for all integers a, b, and c, so a, b, and c are integers. If a is a factor of b and a is also a factor of c, so it's a factor of those two different numbers, then a is a factor of their sum. Then a is a factor, that says factor, of the sum b plus c. The same thing is applied to polynomials. So if a of x is a factor of b of x, and a of x is also a factor of c of x, so it's a factor of those two things, then a is a factor of their sum. A of x, or b of x plus c of x. Sorry, that's terrible handwriting. So let's use real numbers for that. So 3 is a factor of 24. We all know that. We also know 3 is a factor of 12. Therefore, 3 must be a factor of their sum. So that means 3 is a factor of 24 plus 12. which is 36, which it is, so that should make sense. So that holds true for any integers a, b, and c, and for polynomials as well. Okay, we are going to skip example 9. It is another proof using contradiction, but because we didn't do chapter 1 of our book, which is on proofs and counterexamples and things like that, we're just going to skip that for now. But if anyone has an extra special amount of interest in that, I'd be happy to go over it with you. Okay, so examples 10 and 11 really is kind of the summary of what I want you guys to be able to do out of section 4.1. So we're applying all of these theorems and ideas about divisibility and factors to polynomials. So we have two polynomials, a of x, which is x minus 2, b of x, x squared minus 4, and c of x, so three polynomials, x squared plus 8x minus 20. It is saying first to show that a of x is a factor of b of x and c of x. That's two different things we need to show. So I want to show that a of x is a factor of b of x first. To do that, I need to show that I can rewrite b of x as a of x times some other polynomial. So, and which we can do, but it's just a matter of showing it. So all of this is more like convincing the reader, convincing someone that a of x is a factor of b of x. To do that, so b of x is x squared minus 4. I want to show that I can write x squared minus 4 as a multiple of a of x and something else, which a of x is x minus 2. And what would that something else have to be? That would have to be x plus 2. So this equals a of x, times some other polynomial x plus 2. So we've shown, yes, I can write b of x as a of x times some other polynomial. So this line is that proof. That's all it takes. Now I want to show that a of x is a factor of c of x, so it's going to be a separate statement. So if a of x is a factor of c of x, well then I need to show that c of x equals, and c of x is x squared plus 8x minus 20. I need to show that that is a of x times some other polynomial. Well, a of x is x minus 2. Well, what other polynomial will I multiply to x minus 2 to get this? This is kind of, it's just like reverse factoring. Think of it in terms of factoring. If I was going to factor this, I would ask what two numbers multiply to negative 20 and positive 8. And hopefully 10 and negative 2 come to mind. The negative 2 is already right here. We were already told that that's, we're hoping that's one of the factors because we're told to show it. So it's going to be a factor, and that other factor would have to be x plus 10. So that's all it takes to show example A. Show that a of x is a factor of b of x. We've shown that here. And show that a of x is a factor of c of x. We've shown that here because we've written both b of x and c of x as a of x. So many a's and b's. Okay, this is our a of x in both of them times some other polynomial. So we've done that. Now part B is saying that show that b plus c of x can be expressed as a of x times p of x. So there's so many different letters and x's, and it's just overwhelming at first. So instead of b of x plus c of x, let's write what that actually is. Well, here's b of x squared minus 4. X squared minus 4. And add c of x to that, which is this whole thing. So let's add that. Actually, I'm going to erase, I'm going to be more specific here. I'm going to write b of x plus c of x. Now I'm going to rewrite what that actually is. X squared minus 4 plus x squared plus 8x minus 20. So I have that, but what is that really? Let's simplify. 2x squared plus 8x, and then minus 4 minus 20. That's negative 24. Okay, so that is b of x plus c of x, and I want to show that I can rewrite that as a of x, which is x minus 2 times some other polynomial. Basically, I want to multiply x minus 2 out of that. So basically we're going to factor, and we're basically being told ahead of time that x minus 2 is one of those factors. Well, we can factor 2 out of everything here. 2 times x squared plus 4x minus 12. Now the last step is just factoring this one more time to prove that one of those factors is a of x, because that's what we were told to show. So don't forget that 2. And then we want to show that we can write that as a of x, which is x minus 2. And then we just need to figure out what that other polynomial is. So what do I factor if I factor x minus 2 out of that? Well, what two numbers multiply to negative 12 and add to 4? That would be plus 6 minus 2. And again, we have that minus 2 already. So here's our a of x, which means my other polynomial is, really, I would multiply this 2 to both of those things. So we've shown that this equals a of x, which is x minus 2, times some other polynomial, 2x plus 12. And we're finished. So it doesn't seem like all we've done is just rewrite and simplify and then refactor. So we've shown that this sum, just to summarize, we were asked to show that that sum, which equals this, which simplified to that, which factored to that, which really factored to this, which is a of x, x minus 2, times p of x, some other polynomial. So let's do one more of those examples. Hopefully seeing all these again will just streamline the process a little bit. So again, we have 3 polynomials, p of x, q of x, and r of x. The first thing we want to show is that p of x is a factor of both q and r. So that's one thing at a time. So first show that p of x is a factor of q of x. If that's true, then I should be able to write q of x as p of x times some other thing. Well, q of x equals x squared plus 7x plus 12. And we want to show that that is a factor, that p of x is a factor of that. Well, p of x is x plus 3. So to prove that p of x, this, is a factor of this, all I have to show is that this times some other polynomial will get me q of x. Well, what is that polynomial? It's just factoring what multiplies to 12 adds to 7. That'd be x plus 3 and x plus 4. So that's it. We've shown p of x is a factor of q of x. Now we want to show p of x is a factor of r of x. So now we'll use the same thing but with r of x. And all I need to show is that basically I can factor r of x, which is x squared minus 5x minus 24. And if I want to show p of x, which is x plus 3, I need to show that I can factor that out if it's a factor. Well, it multiplies to negative 24 and adds to negative 5. That would be negative 8 and positive 3. So now I've shown, because I've rewritten r of x as p of x times something else, then p of x, or q plus 3, must be a factor of r of x. Now the last one is, again, showing that the sum of q and r can be rewritten as p of x times some polynomial. So just start with what we have. Show that q of x plus r of x. Okay, well, what is q of x plus r of x? That is x squared plus 7x plus 12 plus r of x, which is another x squared, minus 5x minus 24. Okay, so that's their sum. Basically, we just want to simplify it and then factor it to show that it's p of x, which is this. Basically, you just want to simplify this and factor x plus 3 out of it, and then that proof will be done. We'll have shown that. So let's simplify. So I have 2x squared plus 7x minus 5x, so that's plus 2x, and then plus 12 minus 24, so minus 12. Okay, that's what their sum really equals when we simplify, and we want to show that x plus 3 is a factor of that. So let's factor it. Well, we can factor out a 2, and we get x squared plus x minus 6, and we can factor this one more time, and we get 2 times, well, it multiplies to negative 6, adds to positive 1. The fact that we were told to show x plus 3 as a factor should be a huge like red flag, green flag, whatever, that x plus 3 is going to be one of those factors. What's the other factor, though? What multiplies to negative 6 and adds to 1? So that would be 3 minus 2, so x minus 2. So now all we need to do is rewrite it and show that p of x times some other polynomial. Again, p of x is x plus 3, so that's x plus 3, and that other polynomial is, we would distribute this, 2x minus 4. So we have shown that a of x, right here, is a factor of q of x plus r of x. Simply by writing out what is q plus r, simplify it, factor it, and then we see that it is in fact a factor. So this section is a little weird and it's confusing because we're not solving for anything. It's more about showing or convincing or proving that numbers are factors of other things or something is a multiple of something. So this is about the process of showing that. Not necessarily solving, but just convincing the reader that something is a factor.